In this section, we want to look at geometric sequences, and recall that a geometric sequence is one in which each term comes from the previous term by multiplying by the same amount each time. Now, the general term for a geometric sequence is a sub n equals a sub 1 r to the n minus 1. R, remember, is called the common ratio. A sub 1 is the first term. So it's the first term times r to the n minus 1. The sum of the first n terms, if you want to add up the first n terms of a geometric sequence, that's s sub n, and that's equal to the first term times this quantity, r to the n minus 1, divided by r minus 1. Now, there's a third formula for the sum of an infinite geometric sequence that we can use occasionally. These two formulas we can use all the time. So first I want to go to the board and practice using these two formulas. So first of all, for problems number 1 and 2, the question is, are these geometric sequences? Well, let's see. To go from 1 to 5 with multiplication, I would multiply by 5, multiply 5 by 5 again, I get 25, multiply 25 by 5, and I get 125. So the answer here is yes, and in fact, the common ratio r is equal to 5. So this is a geometric sequence, and the common ratio r is equal to 5. How about problem number 2? To go from 1/2 to 1/6, I would have to multiply by 1/3. 1/2 times 1/3 is 1/6. Then 1/6 times 1/3 is 1/18, and 1/18 times 1/3 is 1/54. So this is, in fact, a geometric sequence, and in this case, r is equal to 1/3. So yes, this is a geometric sequence, and in fact, r is equal to 1/3. Now, the next problem I want to do, we're going to be given a sub 1, the first term, given r, the common ratio, and then asked for some other information about the sequence. Let's take a look. Problem number 3, suppose a1 is equal to 4, r is equal to 3. Let's find a sub n. Well, a sub n will always be a1 r to the n minus 1. That's the formula that we want to have memorized. a1 is 4, and r is equal to 3 to the n minus 1. So 3 is raised to the n minus 1. You don't want to multiply it by 4. That is the formula for the nth term of that geometric progression. The 20th term then will be 4 times 3 to the 20 minus 1. That will be 4 times 3 to the 19th. Now, 3 to the 19th power, that's going to be a pretty large number, so I wouldn't want to evaluate it unless I had a calculator, and even then my answer would come out to be an approximation, probably in scientific notation. So we can just leave it this way, 4 times 3 to the 19th power. Now, how about the sum of the first 20 terms of this progression? Will be equal to the first term, a sub 1 times, okay, so this is a sub 1 times r to the n minus 1 divided by r minus 1. So I'll just substitute in a sub 1 is equal to 4, r is equal to 3 to the nth power, whoops, and n is 20 in this case, so 3 to the 20th minus 1, all divided by r minus 1. Now let's see, r minus 1, 3 minus 1 is 2, goes into 4 twice, so I end up with just 2 times 3 to the 20th minus 1. Whoop, and that's an equal sign. Sorry, I'm running out of space, so I had to write it this way, but it's 2 times 3 to the 20th minus 1 for the sum of the first 20 terms of this geometric progression. So it's the first term times this quantity, r to the nth minus 1, divided by r minus 1. So when I put r equal 3 in, 3 minus 1 comes out to be 2. 2 divides into that 4 twice. That's where that 2 came from. Now, 3 to the 20th minus 1, that's a pretty large number, so I can just leave it in this form right here. If I had a calculator, I could get a decimal approximation to it. Okay, let's go on now and look at the next problem. Problem number 4, we have find a sub 10 and s sub 10 for square root 2, 2, 2 square root 2, so on and so forth. So you can see that the common ratio right here is going to be square root 2. I'll multiply square root 2 by square root 2, and I get 2. 2 times square root 2 is going to be 2 square root 2, so on and so forth. So my common ratio r is equal to square root 2. My first term, a sub 1, is also equal to square root 2. So my 10th term, a sub 10, is my first term, square root 2, times the common ratio, square root 2, raised to the 9th power. Square root 2 to the first times square root 2 to the 9th is square root 2. It's square root 2 to the 10th power. Okay, square root 2 is 2 to the 1/2. 2 to the 10th is going to be 2 to the 5th power. That's 2 to the 1/2 to the 10th. I multiply exponents, I get 2 to the 5th, and so that comes out to be 32. So if I want to find the 10th term of this progression, it's the first term, square root 2, times the common ratio of square root 2 to the 9th power. That's a power 1 less than the term number, and so then I have square root 2 to the 10th power. Square root 2 is 2 to the 1/2 to the 10th. Multiply exponents, and I get 2 to the 5th. That's 32. Now, what I want to do next is find the 10th term. I want to find the sum of the first 10 terms of this progression. Okay, the sum of the first 10 terms then is going to be S sub 10 will be equal to the first term, A1, times R to the 10th minus 1 divided by, R minus 1. Okay, so the first term is square root 2 times square root 2 to the 10th minus 1, all divided by square root 2 minus 1. And so, let's see, I know what that square root 2 to the 10th power is. That's that 32. So I get square root 2 times square root 2 to the 10th. I already did that. 32 minus 1, all divided by square root 2 minus 1. So that's square root 2 times 32 minus 1 is 31, all divided by square root 2 minus 1. I'm just going to leave it like that. We could, if we wanted to, rationalize this denominator by multiplying by square root 2 plus 1 over square root 2 plus 1, but I just want to leave it like this, square root 2 times 31 over square root 2 minus 1. So that is not a nice looking formula, but that is the sum of the first 10 terms of this sequence right here. So if I write out all 10 terms and add them all together, I'm going to get the thing that's equivalent to that. Okay, next I want to look at a formula that we can use to find the sum of the terms of an infinite geometric sequence. Let's take a look at that formula. This formula says that if our common ratio R has an absolute value less than 1, then big S here, just capital S, the sum from I equals 0 to infinity of A sub 1 R to the I, which is the first term plus the first term times the common ratio plus the first term times the common ratio squared, so on and so forth as far as we want. That is, the sum of all the terms in this sequence is equal to A sub 1 over 1 minus R. Now, if you want to see the derivation of this formula, you have to look in the book. But it is a nice, simple formula. The only requirement is that the absolute value of R be less than 1. If it is, we simply take the first term, divide by 1 minus R, and that is this infinite sum right here. So let's go to problem number 5 now and see if we can get an example of how we use this. So here I have a geometric series. This is where I'm adding the terms of a geometric sequence. I can see that I multiply 1/2 by 1/2, I get 1/4. Take 1/4, multiply by 1/2, I get 1/8. So in this case, R is equal to 1/2, and the first term, A sub 1, is also equal to 1/2. So according to my formula then, the sum of all the terms is going to be the first term, A1, over 1 minus R. I substitute in, I get 1/2 over 1 minus 1/2. That's 1/2 over 1/2. 1/2 divided by 1 minus 1/2 is 1/2. That's just the number 1. So in fact, it's true that 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32, so on and so forth, that infinite sum converges to, or we might say adds up to, just the number 1. So the sum of all these numbers right here, this is an infinite geometric sequence. R, the common ratio, has an absolute value less than 1, so I can use this formula. It comes out just 1. Let's take a look at another example that uses the same formula. Show that 0.444 is equal to ... is equal to 4/9. So show that this repeating decimal right here is the same as the number 4/9. Well, let's see. 0.444 with the dots is equal to 4/10 plus 4/100 plus 4,000 plus so on and so forth. That's 4/10 plus 400 plus 4,000, so on and so forth. I end up with A1 equal to 4/10 and R, the common ratio, equal to 1/10. That is, I multiply 1/10 times 4/10, I get 400. Times 1/10 again, I get 4 over 1,000. Times 1/10 again, that'll move me over 1 decimal point each time. So a sub 1 is 4/10, r is 1/10. So s, my big sum, is going to be equal to the first term, 4/10, divided by 1 minus r, and r is equal to 1/10. So 4/10 divided by 10/10 minus 1/10, which is 9/10. 4/10 divided by 9/10 is exactly 4/9. Now, if you take 9 and divide it into 4, using long division or whatever, you're going to get 0.4444. You just get this repeating decimal, 0.444, with all the dots. So you can see that this formula gives us results that are consistent with what we already know about just the number 4/9. 4/9 is this repeating decimal, and if I look at it like an infinite geometric series here, with a1 equal to 4/10 and r equal to 1/10, apply my formula, I end up with that 4/9, which is consistent with what I expect to get. So in this section, we've taken a look at geometric sequences and some geometric series.